Imagine you're an engineer in 1983. You've just spent 3 weeks designing a tiny, intricate plastic part for a new prototype. But to actually see it, feel it, and test it, you have to wait weeks for a machine shop to cut a custom steel mold. If your design is just 1 millimetre off when it finally arrives, you have to throw it away and start the whole process all over again. This tedious, heartbreaking bottleneck was exactly what frustrated a young, late-night lab engineer named Chuck Hull. Hull had a sudden, brilliant flash of insight. What if, instead of cutting material away, he could use light to grow an object? He used ultraviolet light to cure thin layers of liquid plastic, printing them directly on top of each other until they formed a solid part. In 1983, he successfully printed the world's very first three-dimensional object, a small, unassuming black cup. Unknowingly, Hull had fired the starting gun for a manufacturing revolution, shifting humanity from subtractive to additive engineering. Today, this core technology has exploded from a simple prototyping tool into an industrial powerhouse, transforming the modern world. Before we dive into the deep mechanics, take a look at the motion in a modern desktop printer. Notice the synchronized dance between the stepper motors, the belts, and the extruder carriage. What you are seeing is a digital brain controlling physical reality with sub-millimetre precision. Every micro-step the motor makes corresponds to a precise amount of material being extruded. It is a masterclass in electromechanical engineering, turning G-code, the language of machines, into a physical, tangible object. At its absolute core, any 3D printer relies on the exact same fundamental principles of computer numerical control, or CNC. A digital 3D model is mathematically chopped by software into hundreds or thousands of horizontal, two-dimensional layers. The printer reads these layers as a set of precise coordinates, moving along the X, Y, and Z axes to build the part. But while the movement geometry is identical, how the material is actually formed divides the technology into three distinct methods. The first is FDM, or Fused Deposition Modeling. This is the version most people are familiar with from desktop machines. It works via material extrusion, pushing solid plastic filament through a heated nozzle to melt it into a semi-liquid state. The nozzle deposits this bead of plastic along a precise path, where it rapidly cools and fuses to the layer beneath it. The second method is Chuck Hull's original breakthrough, SLA, or Stereolithography, which uses chemistry instead of heat. A liquid vat is filled with photopolymer resin that reacts instantly to specific, high-precision wavelengths of ultraviolet light. An ultraviolet laser sweeps across the liquid surface, triggering a chemical reaction that polymerizes the liquid into a solid layer. The third titan is SLS, or Selective Laser Sintering, which is used to build parts that can survive inside a jet engine. A roller spreads a micron-thin layer of engineering nylon or titanium powder across a high-temperature build platform. A powerful high-wattage laser then shoots down, sintering or completely melting the powder particles together into solid metal. Choosing the right material for these printers is an engineering discipline all on its own. For FDM, we are looking at the glass transition temperatures of polymers like PLA, ABS, or high-performance polycarbonate. For SLS, we are dealing with particle size distribution and thermal sintering windows. If the powder is too coarse, the surface finish is rough. If the laser is too weak, the part lacks structural integrity. It is a constant balancing act between heat, friction, and chemical bonding. This brings us to a core engineering question. Why choose 3D printing over traditional, highly optimized factory production lines? The first massive superpower is complexity for free. In traditional machining, intricate geometries mean skyrocketing tool costs. With 3D printing, a hollowed-out lattice costs the same, or less, to print than a solid block because it uses less material. This allows aerospace engineers to utilize topology optimization, mimicking organic bone structures to place material only where stress travels. The result is aircraft and rocket components that are 40% lighter, yet just as strong, drastically cutting global fuel consumption. The second superpower is mass personalization. Traditional manufacturing requires rigid molds that make custom, one-off parts impossible. But in modern medicine, engineers can take raw data from a hospital CT scan and convert it directly into a 3D digital mesh. An industrial printer can then manufacture a titanium cranial or spinal implant shaped perfectly to that specific patient's unique anatomy. Beyond the design of the part itself, 3D printing is fundamentally changing the global supply chain. In the past, companies needed massive warehouses to store thousands of spare parts. Today, we are seeing the rise of digital warehousing. Instead of shipping a replacement gear for a tractor across the ocean, a company simply emails a secure file to a local hub, and the part is printed on demand. This reduces carbon footprints, eliminates shipping delays, and ensures that legacy equipment can stay operational for decades longer than ever before. So, where is this technology going next? The absolute horizon of additive manufacturing sounds like pure science fiction. We are moving rapidly into the era of bioprinting, using specialized bioinks composed of living human cells and cellular matrices. Scientists are successfully printing living tissue patches and blood vessels, paving the way toward future transplantable organs. At the other end of the scale spectrum is large-scale structural printing, using massive robotic arms on construction sites. These colossal gantry systems are actively printing entire houses out of specialized concrete composites in a matter of days. This frontier drastically reduces material waste on site, cuts manual labor hours, and allows for sweeping, optimized architectural designs. It is important to remember that the print is rarely finished the moment it leaves the build plate. Every additive process requires an afterlife. For metal parts, we have to deal with support removal, thermal stress relief in industrial ovens, and CNC machining of critical interfaces. For resin parts, it is all about curing times and solvent washes. Understanding these secondary processes is just as critical for a lead engineer as the printing itself, because this is where the final quality of the product is truly forged. When Chuck Hull watched his first thin layer of resin cure 4 decades ago, he was just trying to solve a workflow problem in a quiet lab. But that single, modest experiment ignited a fire that has fundamentally rewritten the rules of what we can create. We have officially transitioned into an era where our physical world is no longer limited by traditional factory tools or expensive, rigid manufacturing lines. Today, if you can imagine it and draw it on a screen, you are only a few clicks away from holding it in your hands. We have moved from a world of make to stock to a world of make on demand. The most exciting part of this revolution is that it is no longer just for professional engineers in high-tech labs. 3D printing is becoming a tool for everyone. From hobbyists building custom home repairs to artists creating sculptures that would have been impossible a decade ago. It is democratizing creativity, allowing anyone with a computer to become a manufacturer. As these machines become faster, cheaper, and more capable, the only remaining limit is our collective curiosity. So, as you look at the world around you, start asking, what would you build if you could make anything one layer at a time?